A freight train a mile long rolls through Nebraska at 3 a.m., and somewhere near the middle, one car rides different from the rest. It's empty. No cargo, no revenue, just dead weight bouncing lighter on the rails while 100 loaded cars grind forward around it. The railroad knows it's there. Hauling that car across 1,000 miles burns real fuel, and the company pays without flinching, because removing it would cost something far worse. The reason starts with a single steel pipe running the entire length of the train, a design that hasn't fundamentally changed since the 1800s. A freight train looks like one machine, but it isn't. It's hundreds of individual vehicles chained together, each one carrying its own weight, its own momentum, and its own braking system. The only thing unifying all of them is a single steel pipe running from the locomotive to the last car, filled with compressed air. When the engineer moves the brake handle, the command doesn't reach every wheel at once. It travels through that pipe as a pressure wave, and pressure waves take time. The cars at the front receive the order first. Cars in the middle get it a moment later. Cars at the rear might not respond for several seconds. On a short train, those seconds barely matter. On a train stretching more than a mile, they matter enormously, because while the front of the train is already slowing down, the rear is still pushing forward at full speed. Thousands of tons of steel and cargo, still carrying every bit of momentum they had before the brakes were called, now shoving into the cars ahead of them. The forces this creates are violent and constant. As cars compress together, railroaders call that buff force. As they stretch apart, that's draft. Every freight train on the continent lives with both on every trip, and the system is built to absorb them. The couplers flex. The slack between cars gives each vehicle room to adjust. Engineers learn to apply brakes gradually, feeding the command into the pipe in stages rather than all at once. Because slamming the brakes sends a shock wave through the train that the rear cars answer with a surge of their own. The whole system works as long as every car in the chain plays by roughly the same rules. But those rules depend on one critical assumption, that every car weighs roughly the same. The moment one doesn't, the physics changes completely. A loaded hopper car full of grain or coal can weigh well over 100 tons. Empty, that same car might weigh 30. Put the empty one between two loaded ones in a mile-long train, and it becomes the weak link in a chain that doesn't tolerate weakness. When the brakes hit, every car in the train begins decelerating, but not equally. The loaded cars carry enormous momentum. They resist the change, slowing down gradually under the weight of their own cargo. The empty car has almost nothing holding it back. It reacts faster, lurching against the coupler ahead of it, while the loaded car behind it is still grinding forward. Imagine a line of people sprinting while holding hands. If everyone weighs roughly the same, the group slows together, but drop someone half the weight of everyone else into the middle of the line, and they get yanked in both directions every time the pace shifts. That's what happens inside a train. The empty car doesn't just respond differently. It becomes a point where forces concentrate, and those forces don't stay local. They ripple outward through the couplers, car by car, amplifying as they travel. What started as a small mismatch near the middle of the train can build into a handling problem the crew feels in the locomotive half a mile ahead. A strange pull or shudder traveling through the controls with no visible source. Under the worst conditions, those force spikes can damage couplers, derail cars, or create the kind of unpredictable train behavior that turns a routine trip into an emergency. The empty car isn't just dead weight. It's a physics liability riding in the middle of a system designed around uniformity, and every railroad on the continent knows it. The obvious fix is to build a braking system smart enough to make weight differences irrelevant. Someone did exactly that. It worked beautifully, and the industry walked away from it. The technology is called electronically controlled pneumatic braking, and it solves the problem almost perfectly. Instead of sending a pressure wave crawling through a mile of steel pipe, ECP braking sends an electronic signal down the train at nearly the speed of light. Every car receives the command at the same instant. Every brake applies simultaneously. The air pressure wave that once gave the front of the train a head start and left the rear shoving forward blindly is eliminated in a single upgrade. The results were exactly what engineers predicted. Stopping distances shrank. Train handling smoothed out. The violent buff and draft forces that ripple through conventional trains became manageable and predictable. Light cars and heavy cars braked together instead of fighting each other. The empty car problem, the one that has plagued freight railroads since the first mixed-weight trains rolled, was functionally solved. And then the railroads looked at what it would actually cost to deploy. North America's freight rail network doesn't belong to one company. Hundreds of thousands of freight cars circulate across the continent, owned by different railroads, leased by different shippers, maintained in different yards. A single car might start its week on one railroad, get handed off to a second, and finish on a third, 1,000 miles from where it began. Every one of those cars would need new electronics, new wiring, new brake valves. Every locomotive would need compatible control systems. Every maintenance shop would need new tools and procedures. Every crew would need retraining. And every competing railroad would need to agree on a single standard simultaneously across an industry that has never agreed on anything quickly. The price tag climbed into the billions. Not billions spread across decades of gradual adoption, but billions required upfront before the system could function at all. Because ECP braking only works if every car in the train has it. One conventional car breaks the chain. The technology couldn't phase in gradually. It needed total commitment or nothing, and the industry chose nothing. The braking pipe stays. The empty car stays. But this still leaves the simplest version of the question unanswered. If the empty car is a known liability, why not just pull it from the train before it ever leaves the yard? Uncoupling a railcar takes minutes. A crew member pulls a lever, the knuckle opens, and the car separates. Physically, it's one of the simplest operations on a railroad. Operationally, it detonates a chain reaction that can paralyze a yard for hours. The moment a car leaves a train, federal regulations take over. The train's brake system has changed. Air pressure dynamics through the pipe have shifted. The weight distribution is different. Before that train moves another inch, federal law demands a full brake test and inspection, not a quick check. A methodical, car-by-car procedure where inspectors walk the length of the train, verifying that every brake responds correctly, every coupler is secure, every connection in the airline holds pressure. On a train with 100 cars, this alone can consume hours that the railroad doesn't have. But the inspection is only the beginning of what breaks. The train's documentation must be rewritten to reflect the new configuration. Crew assignments may need to change if the modified train falls under different handling rules. The car that was removed now sits in the yard, occupying track space that was allocated to something else, and yards operate on margins thin enough that a single unplanned car can force other trains to reroute or wait. Meanwhile, the train that stopped to shed one empty car is burning locomotive fuel while it sits. Crew hours are ticking. The slot this train was supposed to fill at the next interchange point is slipping away, and the railroad waiting on the other end is now adjusting its own schedule to compensate. One uncoupling doesn't just delay one train. It sends a ripple through a network where every movement is sequenced against every other movement, and a single disruption can cascade across a continent's worth of tightly scheduled operations. The delay compounds. The cost multiplies. And at the center of all of it sits one empty car that weighs almost nothing, whose only crime was being lighter than its neighbors. Every railroad runs this calculation constantly, weighing two costs against each other, and the answer almost never changes. On one side of the scale sits the visible cost. Hauling an empty car across 1,000 miles burns fuel. The locomotive has to pull that extra weight up every grade, break it down every descent, and drag it through every curve. It's real money, and no railroad pretends otherwise. But a single empty car on a train already weighing tens of thousands of tons is a rounding error in the fuel bill. The locomotive barely notices. The additional drag is so small relative to the total consist that it vanishes into the noise of a journey already consuming thousands of gallons of diesel. On the other side sits the invisible cost, and it dwarfs everything on the visible side. Pull that car, and the inspection clock starts. Crews idle while inspectors walk the train. Yard space fills with a car that wasn't supposed to be there. The train misses its interchange slot, and the receiving railroad adjusts its own schedule to absorb the delay. That adjustment bumps another train, which delays a shipment, which triggers a penalty clause in a contract the railroad signed months ago. The invisible cost doesn't just add up. It multiplies, feeding on itself as each disruption creates the conditions for the next one. This is the calculation that governs freight railroading, and it runs every single day across every major railroad on the continent. The empty car costs less than the chaos of removing it. Not slightly less, dramatically less. What looks like waste from the trackside is actually the cheapest option available, and the railroads arrived at this answer not through theory, but through decades of watching what happens when someone tries the alternative. The empty car isn't a failure of the system, it is the system working as intended. Railroads didn't stumble into this logic. They built it deliberately, over more than a century of learning what actually breaks when you chase perfection instead of reliability. That empty car rolling through the night isn't carrying nothing. It's carrying flexibility. The ability for a railroad to assemble a train once and run it across a continent without stopping to reconfigure every time the cargo mix changes. It's carrying compatibility, a guarantee that any car from any owner on any railroad can slot into any train without demanding special treatment. And it's carrying something no engineer can design from scratch: the accumulated lessons of more than a century of operations, every derailment investigated, every delay traced to its source, every shortcut that looked clever until the network punished it. Railroads learned long ago that perfection on a single trip is worth less than reliability across 10,000 trips. A system that tolerates small inefficiencies and keeps moving will always outperform one that chases theoretical optimization and stalls. The empty car is the physical expression of that principle, a compromise riding on steel wheels, absorbing a tiny cost to prevent a massive one. So the next time a freight train passes and you spot that one car riding light near the middle or the rear, bouncing slightly higher on the rails than everything around it, carrying nothing visible, you're not looking at a mistake. You're looking at a decision made by people who understand that the most expensive thing a train can do is stop. That car earned its place not by carrying cargo, but by keeping everything else moving. And yet, the empty car isn't even the strangest cost a railroad chooses to pay. Somewhere right now, a locomotive is parked in a yard with its engine running, burning diesel around the clock, because the cost of shutting it down is even harder to believe. Those engines idle for days, sometimes weeks, burning hundreds of gallons of diesel while doing absolutely nothing, because the fluid inside a locomotive's cooling system can gel in cold weather, the engine block can crack, and restarting a dead locomotive demands specialized crews, equipment, and hours the railroad would rather spend moving freight. An entire industry chooses to burn fuel around the clock rather than risk the cost of a cold start. That story, the economics of never turning off a machine, is next. And if this is the kind of engineering you want to understand, the subscribe button is right there.